Welcome to the Deep Dive. Today we're diving into a really foundational concept in electricity. It's one that often sounds a bit daunting, maybe, but it's surprisingly intuitive once you break it down. And you actually asked us to explain this at a beginner's level, focusing on clarity, making it approachable. So that's exactly what we're going to do. Our main guide for this deep dive is Jen Byung Chil's excellent book, Yon Jo Non. That translates roughly to Authentic Beginner's Walk Through Electricity, and it's published by Gilbert Publishing. It's a fantastic source, really, because it's genuinely built to make these complex electrical topics accessible, perfect for getting the basics down. So, our goal today, demystify how electrical energy gets stored. We're zeroing in on a key component called a capacitor, and its ability, capacitance. Think of this as your shortcut, yeah? Your way to understand a vital part of nearly every electronic device you own without getting totally bogged down in jargon.
Yeah, and what's really fascinating, I think, is just how often we interact with tech that uses these principles every single day, without even thinking about it. We'll kick off with a very relatable analogy from our source. It'll help us grasp not just what these things do, but crucially, why they matter so much.
Okay, let's unpack this.
Yeah.
We'll use something really familiar, especially if you know Korean culture. Rice. Many of us eat it daily, right? But have you ever really stopped to think about how to store the most rice possible in just one bowl? Our source brings this up with a brilliant, simple question. How do you get more rice into a rice bowl? Your first thought is probably right on the money. Use a bigger bowl.
Right.
Simple. A larger bowl holds more.
Right.
That's variable number one.
Seems obvious maybe, but it's fundamental.
Capacity.
Right. The physical size of the container dictates how much fits. And we'll see this exact principle mirrored in electrical components.
But hang on, there's another trick, isn't there?
Yeah.
Even if you have the same size bowl, you can press the rice down, compact it. Think about making that perfect scoop for sushi, maybe?
Yeah, pack it in tight.
By applying pressure, you kind of squeeze out the air gaps. And you can fit a surprising amount more in the same bowl.
Absolutely works. And this idea, this pressing down, it's really key for where we're going. The source even gives us this fun little, simplified formula. Rice, bowl size, X
pressure. It illustrates it nicely, doesn't it? If you want to store a lot of rice, you've got two main options. Bigger bowl or press harder.
Or both.
Or both, yeah. It shows capacity isn't just about volume, but also how efficiently you use that space.
Okay, so rice storage mastered. Now let's make that leap.
Yeah.
From the kitchen bowl to an electrical circuit. How does this whole idea of capacity and pressing pressure translate when we're talking electrons? Storing electrical energy? Perfect transition. Because just like storing rice efficiently, we often need to store electrical energy. And this is where the analogy perfectly sets up the star of our deep dive, the capacitor. Now, when you think about storing large amounts of electricity for, a long time, we usually think batteries, right? Chemical reactions doing the work there.
Right. Batteries are for the long haul.
Exactly. But what about storing small amounts of electricity, maybe for just a very short time, or for really quick bursts, like charge up, discharge really fast?
Ah, okay. So batteries aren't always the answer for that quick stuff.
Not always ideal, no. And that's where the capacitor shines. Our source notes it's also called a condenser, or sometimes an accumulator, on Korean. But at its heart, just like that rice bowl holds rice grains, a capacitor stores electrical charge. That's any, and that charge holds potential energy.
So they're not quite batteries, more like tiny, super fast electrical banks. Good for quick deposits, quick withdrawals of energy. Yeah. That actually makes a lot of sense, especially for a beginner trying to grasp this. The book also mentions different flavors of capacitors based on what they're made of. Why so many types? Are some better for certain jobs?
Indeed, there's a whole variety, and understanding the differences really highlights their versatility. Our source mentions types like electrolytic, tantalum, ceramic, mica, mylar, quite a list.
Wow, okay.
Each one is sort of optimized for specific jobs, and it mainly comes down to the materials used inside and how they're built. For example, you've got electrolytic capacitors. They generally give you a lot of storage, high capacitance, and a pretty small package. Great for things like power supplies where you need to smooth things out.
Okay.
But, big caveat, they are polar. You have to connect them the right way around. Plus and minus matter a lot.
Okay. The polarity thing, we'll come back to that. What about others?
Then you have things like ceramic capacitors. Often smaller, less capacitance maybe, but they're fantastic at high frequencies. Really good for filtering out electrical noise. Very stable, very fast.
Noise filtering, interesting.
And film capacitors, like Mylar types, known for precision, stability. You find those in audio gear, sensitive timing circuits, that sort of thing. So yeah, each material brings trade-offs. Size, cost, how stable they are, voltage limits, speed. It gives engineers a whole toolbox to pick from.
That's a great way to put it, a toolbox.
Mm-hmm.
Okay, so let's dive a bit deeper now. How do these things actually store the electricity? How does the bowl size and pressing down work electrically? What's happening inside, fundamentally? No magic.
Right, no magic, just physics. And the principle is actually quite elegant, pretty simple to picture. Imagine the most basic capacitor possible, just two conductive plates. Think metal sheets usually, placed incredibly close together.
Okay, two metal sheets close.
But, and this is the absolute key, they are separated by a tiny gap. And crucially, that gap is filled with an insulating material.
An insulator. So something that doesn't conduct electricity.
Exactly. It stops the electricity from just jumping across. Sometimes the gap is just air, but usually there's a specific insulating material put in there. We call it a dielectric.
Dielectric, okay.
Its job is vital. Make sure electricity cannot flow directly from one plate to the other. It's like a solid wall preventing a short circuit.
Ah, okay, so the dielectric is the key barrier. It keeps things separate, but maybe lets them influence each other. Is that where the pressing down comes in? Or the bowl size?
You're getting there. The dielectric actually improves the capacitor's ability to store charge. A better dielectric is like having a stronger bowl, or one designed to hold more under pressure, sticking with our analogy. Now, imagine connecting a power source, like a battery, to these two plates. One plate connects to the positive terminal, the other to the negative.
Okay, hooked up to power.
What happens is electrons, which are negatively charged, get pulled off one plate by the positive terminal of the battery. This leaves that plate with a net positive charge. At the same time, the negative terminal of the battery pushes electrons onto the other plate, so that plate builds up a negative charge.
So one plate goes positive, the other goes negative?
Precisely. You get this buildup of opposite charges on the two plates. And because of that dielectric insulator between them...
They can't jump across.
Exactly. They can't cross the gap and neutralize each other. They're attracted to each other, pulled by the electric field between the plates, but they're stuck, held separate. And that state charge is built up, held apart, creating this electrical tension or potential difference across the plates. That is how electrical energy is stored. It's like our pressed down rice, energy packed into a small space, ready to be let go.
Okay, that makes it click. So they don't let electricity flow through continuously. They gather it. They build up this tension. So what are the practical uses for this temporary, almost instant storage? Where do we actually see this in action in the stuff we use?
Oh, their ability to quickly store and then rapidly release that charge makes them incredibly versatile, super useful. One key function is definitely that temporary charge storage, like a tiny, ready-to-go energy reservoir.
Like for a camera flash.
Yeah.
That sudden burst of light.
Exactly like a camera flash, that intense instant burst, often powered by a capacitor dumping its stored energy very, very quickly, much faster than a battery could manage. Or think about, say, some car stereos. You turn the car off, but the radio might keep its station, or the clock stays on for a few seconds.
Yeah, that happened.
Often that's a capacitor providing that last little bit of power, just for a moment.
Ah, clever. So quick power bursts and little memory backups. Are there other big jobs they do?
Absolutely. Another huge role is protecting circuits and smoothing out power. This is really important. Think about the power from your wall outlet. It's AC, alternating current, right? Kind of goes back and forth.
Okay.
But most electronics need DC, direct current, nice and steady. When you convert AC to DC, the output isn't perfectly smooth. It often has these little bumps, these ripples in the voltage.
Okay, so the DC isn't perfectly flat.
Right. Capacitors act like little sponges here. They absorb the peaks of those ripples and then release charge to fill in the dips. The result, a much smoother, more stable DC supply, which is critical for sensitive electronics.
Like filtering the power, smoothing it out.
Exactly. And they also act as safety nets. Imagine a sudden voltage spike, maybe a fluctuation from the power grid, or even static electricity, a nasty electrical jolt. A capacitor can instantly absorb that excess energy, storing it temporarily. It prevents that surge from frying the delicate components downstream in your TV or your computer. It's like an electrical shock absorber.
Wow, okay, so they're real multitaskers. Quick power, smoothing things out, acting as protection. Pretty amazing for what sounds like a simple component.
Yeah.
So we have these devices storing charge. How do we actually measure how much they can store? Is there a unit for this storage ability, this capacity?
Yes, and this brings us right to the core concept, capacitance, usually. Just like we talked about the capacity of the rice bowl, capacitance is the measure of a capacitor's ability to store electrical charge. More specifically, it's defined as how much charge it can store for a given voltage applied across it.
Okay, capacitance, got it. Is there a symbol, a unit?
Yep, the symbol is C, and the unit is the farad, symbol F, named after Michael Faraday, the brilliant 19th century British scientist.
Michael Faraday.
Right.
Made huge contributions to electricity and magnetism.
Immense contributions. It's fitting this unit bears his name. You know, before modern capacitors, they had things like Leyden jars, these early devices for storing static charge. He built on all that work. But here's the thing about the farad. 1 farad is actually a huge amount of capacitance, way more than you typically need in most electronics.
And really, 1 farad is big.
Enormous, electrically speaking. So in practice, you'll almost always see capacitors measured in much smaller units. Our source points out that 1 farad is equal to 1 million microfarads. That's AF.
A million. Wow.
Yeah. And you'll also see nanofarads, NF, which are 1,000 times smaller than microfarads, and even picofarads, PF, which are 1,000 times smaller again. It's just about using a practical unit for the scale you're working with, you know, like measuring sugar in teaspoons, not gallons.
1 million microfarads in a farad. That really puts it in perspective, especially for beginners. It explains why you see myth written on components all the time. Okay, so we know what they are, how they work, how we measure their capacity. But for someone actually, looking at a circuit board or maybe trying to build something, are there crucial rules, pitfalls to avoid? Especially that plus and minus thing you mentioned.
Ah, yes, that's absolutely vital, practical stuff. Capacitors generally fall into two main categories you have to know about: polar and nonpolar.
Polar and nonpolar. Okay.
Understanding this difference is critical for safety and just for making the circuit work at all. Polar capacitors, like those electrolytic ones we talked about, the ones often good for power supplies, they must be connected the right way around. They have positive, plus, and negative terminals.
When you said they're marked?
Usually very clearly marked, yeah.
Yeah.
Often a strike down the side for the negative lead, or maybe one lead is longer than the other. Typically, the longer lead is positive. If you connect a polar capacitor backward, well, bad things can happen. It can get damaged, overheat, leak, nasty stuff. Or sometimes, yes, even pop or explode. It's startling.
Yikes. Okay, so rule number 1, check the markings on polar capacitors and get the polarity right. Don't connect it backwards.
Absolutely non-negotiable. It's a classic beginner mistake, unfortunately. Lesson sometimes learned with a bit of smoke.
Right. So what about the non-polar ones? Are they safer?
Non-polar capacitors are much more forgiving in that respect. They don't have that positive-negative restriction. You can connect them in either direction in the circuit, no problem. The ceramic ones, film capacitors, they're typically nonpolar. Makes designing with them a bit easier sometimes.
Less chance of accidentally blowing things up.
Pretty much. And circuit diagrams, the schematics, they usually use different symbols for polar and nonpolar types, which helps you identify them. Oh, and just one more thing to add to the mix. Our source also mentions variable capacitors.
Variable, meaning you can change their capacitance.
Exactly. Their capacitance isn't fixed. You can adjust it. Usually by physically turning a knob or a screw. This changes the overlap area of the plates inside, or maybe the distance between them.
Where would you use something like that?
The classic example is tuning circuits. Think old-school radios where you turn the dial to find a station. That dial was often connected to a variable capacitor, changing the circuit's resonant frequency to tune in to different radio waves. Still used today in some applications.
Fascinating. So from fixed to variable, polar to nonpolar, quite a range.
Yeah.
Okay, so what does this all mean for us, the learners? Especially those just starting out, wanting that beginner-level view. We started with rice, right? Rice in a bowl. And now we've kind of unpacked the whole world of electrical energy storage, from basic ideas to how capacitors actually work inside, why we need them everywhere, how we measure them, and even the really crucial practical stuff like polarity. We've definitely taken a deep dive into capacitance and hopefully kept it clear and approachable, just like you asked. So today we've really seen how a simple idea, just storing something, translates into this incredibly important, versatile electrical component. From making your camera flash work, to smoothing out power, protecting your gadgets. Capacitors are these silent workhorses inside countless devices, your phone, the internet infrastructure, everything.
Absolutely. And connecting it back to the bigger picture, if you really want to understand how electronic systems work, grasping these fundamental components like how capacitors manage energy, It's key. It really is. It's a great reminder that even the tiniest parts, the ones you might never even see, play these critical roles in making all our technology function.
So next time you plug something in, or admire the sound from your speakers, or even just notice your car radio keeping its memory for a second, maybe give a little thought to those tiny electrical rice bowls inside quietly doing their job. Makes you wonder, doesn't it? What other seemingly complex electrical bits could be explained with a simple everyday analogy like that? We'd love to hear your thoughts.